Hello, Math Studies students, and welcome to another online lesson. Today we're going to be talking more about derivatives, specifically applying derivatives to various applications. So for applications of derivatives, we're trying to use real-world situations, or at least slightly more real-world, to show how we can actually use our knowledge of derivatives, slopes, maximums, minimums, and things like that in a more real-life application sort of thing. So what we need to keep in mind is, once again, derivatives are slope. And when our derivative equals 0, that means that we have a slope of 0, which can occur at a maximum, and it can also occur at a minimum. When it comes to real world, we're often concerned about maximums and minimums, maximum amount of time it takes us to do something, or the maximum profits, or finding the minimum cost of production, or things like that. So we get very concerned about maximums and minimums. As I showed last class using sign diagrams, we can find maximums and minimums using derivatives without having to make a graph. And that's what we'll focus on doing here on this next problem. The other thing to keep in mind for real life problems is we have to know a lot of other mathematics as well. So this is going to review a whole lot of mathematics right here in this problem. And I will do my best to make sure that I can fit it all here on the screen. So to start with, we have a closed rectangular box. It has a height of y, a width of x, its length is twice its width. It has a fixed outer surface area of 300 centimeters squared. Show that, so the answer is already given here, show that that 4x squared plus 6xy equals 300. All right, well, I see the 300. That was surface area, and that's the only constant I have in this whole problem. So how do I find surface area? Well, I have to add up all the area of each of the surfaces. All of these are like rectangular surfaces. I have the front side, I have the back side, which we can't see, I have the right side, I have the left side, I have the top, and I have the bottom. So all of those sides. You'll notice because it's rectangular, there's always a pair of sides or faces that have the exact same area. And so we really have to find out 3 different faces and then multiply that by 2. So the face on the right, which would be the same as the face on the left, would be the area of x times y. But again, there's going to be 2 of them. The face on the front has the 2x as its width, and then it has the same height as before, so that's going to be 2x times the y, but there's 2 of them, so we multiply that all by 2 and add them together. And the last one would be the bottom side, which would be 2x times another x, and that's all going to be multiplied by 2 as well. And we know the whole thing should equal 300. So let's see if we can clean this up now. So I have 2xy plus 4xy plus 4 from these two 2's here, as well as x times x, which is x squared, and that all equals 300. Now I can combine like terms, which I have right here, which is 6xy plus 4x squared equals 300. And if I just rearrange that, I have the answer that they gave there. So I'm going to erase that work so that I have room for the next part. Now it says find an expression for y in terms of x. So in terms of y means get y alone. I'm sorry, expression for y in terms of x means get y alone, and you're going to have x's in your answer. In terms of, meaning that is what I've used to express my answer, but I want to get y alone. So I take the answer that I just had, the 4x squared plus 6xy. And if we were taking the actual IB test and we didn't know how to show that, we could skip straight to B and utilize this answer for our next part. Now we want to get y alone. So I'm going to start by subtracting the 4x squared. No like terms on the right side, so that's 6xy equals 300 minus 4x squared. I want to get y alone, so now I'm going to divide everything by 6x. Really, we're done. We have an expression for y in terms of x, 300 minus 4x squared all over 6x. Now, if you want to break that up into 2 fractions, that's absolutely fine. If you want to leave it all like that, that's fine too. But we do need to do volume. So I think I'm going to leave that one alone. I'm going to put it over here on the right side. If we need to change it a little bit later on, we can do that. But we've answered the question. An expression for y in terms of x. All right. Now, we're going to go on to volume. It says, hence show that the volume of the box is given by V equals 100 x minus 4/3 x cubed. So, volume. Well, we find volume is equal to length times width times base, or base times height times, or area of the base times the height is another way to do it. So our area of our base would be 2x times that other x, but then our height is y. So it's 2x xy, also known as 2x squared y. There's a lot of variables in there. We have v, we have x, and we have y. The idea is that when we do a derivative, we don't want to have that many variables, and eventually we're going to maximize this box. So we need to get rid of one variable. Look at the answer they gave us. It has 100x minus 4/3 x cubed. What does their answer have that ours does not? Or what does ours have that theirs does not? We have a y involved in ours, and theirs does not. Now, there's lots of other differences as well, but that's the main difference. So we need to get rid of y. If only I knew what y was equal to. And based on our previous work, we do know. We know that y is 300 minus 4x squared all over 6x. So I'm going to rewrite this as v equals 2 times x squared. But instead of writing y, I'm going to take everything that we had over here and plug it in. So I now have 300 minus 4x squared all over 6x. Now I'm going to distribute my 2x squared, or you could even cross cancel right at the beginning. You'll notice that we're multiplying an x squared right here, but we also have an x that we're dividing. So if you want to cancel out that x and one of those x's right away, that's fine, because again, we're multiplying by x's and dividing. That would just leave us 2x that we're multiplying to each and every one of these things. So 2x distributed to the 300 would give me 600x. The 2x distributed to the negative 4x, well, the 2 times the negative 4 gives me negative 8. And then the x times the x squared gives me x cubed. And that's all over 6. And that would be my volume still. I didn't change that at all. Now I look at the answer they have compared to the answer I have. Not quite the same. They don't have the whole thing over 6. So let's divide both terms by 6. So we start with my 600. Let me switch pen color here. So we start with my 600. And we're dividing that by 6. Well, if I have 600 x's and I divide it by 6, I'm left with 100 x's. And then I have 8 divided by 6, or negative 8 divided by 6, which is 8/6, which reduces to 4/3. And then I just bring down my x cubed, so 4/3 x cubed, and now we have the same thing that they had right here. All right. Make some room again. And it says find dv dx. Well, we should have seen that notation before. We're used to seeing it with dy dx, which means find the derivative of y with respect to x, or derivative of y in terms of x. We don't have any y's anymore. We have v's. So it just means do the derivative of v in terms of x. And the derivative of v in terms of x should take us seconds, ideally. So I'm going to write down my v over here. V equals 100 x minus 4/3 x cubed. Well, the derivative, or dv dx, we'll use their notation, the derivative of 100x becomes just 100. And then for the 4/3, I have to remember to take my old exponent and multiply it out front. But if I multiply, you can do it two ways. We could actually show the work. Let's do it that way. So we take the 3 times the 4, which gives me 12 over 3. Again, you can think of this as 3 over 1 as our exponent. We multiply straight across. 3 times 4 is 12. 3 times 1 is 3. Then we lower the exponent down to 2. But 12 divided by 3 gives us negative 4. So we have 100 minus 4 x squared as our derivative of v with respect to x. And so that is part D. Now it says, hence find the value of x and y required to make the volume of the box a maximum. So we want to get the biggest possible box. We still only have this surface area. That was our sort of constraint that we have. So we want to know where this expression here that we just did, this derivative, has a maximum. So that goes to our previous lesson. Wherever there's a maximum, we know our slope is 0. And if our slope is 0, we can set our derivative equal to 0. I'm going to do some erasing over on the right side here to again make room. So I take my derivative that we just did, 100 minus 4x squared, but I want to find out where we have a maximum, so I'm going to set it equal to 0. It's a quadratic, so you could factor this, but we could use a quadratic formula. We could throw it in our calculator and find out where it crosses the x-axis or where it equals 0. Or we could just use some straight algebra because there's only one variable even though it's being squared. So I'm going to add 4x squared to both sides. I'm moving the 4x squared because it was negative. That way I'll have all positives going on here. So now I have 4x squared equals 100. Divide both sides by 4. So I get x squared equals 25. And to get rid of the square, I either take it to the 1/2 power or I can square root. And technically, whenever I do a square root, there's going to be two answers, a positive and a negative. And the square root of 25 is 5. But we're dealing with x, which was a length. Can we have a negative length? No, we cannot. So we know that x has to be 5 centimeters. Now, I didn't make a sign diagram. I could have at this point, and I can do that right now. Sign diagram, again, is where we take all of the spots where our derivative equals 0, which would be 2 of them right here. Let me do that again, because we technically had 2 answers. We had positive and negative 5. If I put those both on a sign diagram here, I would have to check values that were less than negative 5, between negative 5 and 5, and greater than 5, and plugging back into my derivative all the way over here. Well, if I put in a value that is less than negative 5, it means it would be a negative number going in right here. A negative number squared is going to become positive. So let's do something like negative 10. So negative 10 squared gives me 100. 100 times negative 4 is negative 400, and 100 minus 400 is very much a negative answer. So we have negative slopes before x equals negative 5. Between negative 5 and 5, we can pick a value like 0, and if I plug a 0 in for this x, again right here, that'd be 0 squared. 0 times negative 4 gives me 0, and 100 minus 0 is very much a positive answer. And then last but not least, pick a number that is greater than 5, like 10 or 100 or a billion or whatever, and you'll end up getting a value here for this x that is very big and positive. We'll multiply by 4, which will make it 4 times bigger, but notice there's a negative sign in front of that whole thing, so we'll end up having a very negative sort of answer, which makes that last bit negative. So our graph goes down, then it goes up, and then it goes down again. Which one of these would be a maximum? Well, if we're going down and then we're going up, that is a minimum. And then if we're going up here and then we get to the 5 and then we start going down, this would have to be a maximum. So we do know that this is in fact a maximum. I don't know that you necessarily needed to do all that work because of the fact that it was a real life problem and one of our answers was not realistic. And so we knew that this one probably was going to be our maximum all along. Then it says find the y value as well. Well, we can go back to our expression for y, which unfortunately I totally erased earlier, but we can then plug in our x value to find our y. And I'm going to utilize this equation right here since I erased my previous one. And if I plug in my x, let's clean up the left side of the board. I think I can do that. Calculate volume. So right here, I'm going to take my x value, which we said was 5. So I have 4 times 5 squared plus 6 times 5 times y equals 300. Again, if we had the other expression with y alone, this would be a little bit faster, but we get 25 times 4 is 100 plus 30y equals 300. Subtract 100 from both sides. I get 30y equals 200. Divide both sides by 30. And I end up with 15? No, I'm sorry, 7.5. Just going to double check that. And in fact, the answer is, sorry, 6 2/3. Glad I checked that. Also known as 20/3. That would also be centimeters, which would be our y value right here. And then last but not least, it says calculate this actual maximum volume here. And we could have used our volume expression with all x's in it, and then we could just plug in our x value, which is 5, which might still be a smart thing to do because we know that that was a right answer. And if I had made a mistake here on the y and I plug in the y that's incorrect, I'm going to get a wrong answer. This is less variables to deal with. So let's do that. Let's use the volume equation here. So volume equals 100 times our x, which we know is 5, minus 4/3 times 5 cubed. And I would probably just reach for a calculator at this point. And so we get 500 minus 4/3 times 5 to the third power, or 333 1/3 would be an exact answer, and that's volume. So that'd be centimeters cubed. Or if you round to 3 significant figures, it's just 333 centimeters cubed. And that, ladies and gentlemen, is using derivatives to help us find maximums for a slightly more realistic problem. Now, how much of that actually involved derivatives? The first part dealt with old school knowledge from geometry and Math Studies 1, dealing with area. Then manipulating your expressions to isolate a variable. That'd be like Algebra 1 and Algebra 2. Then we had some substitution, which would also be like Algebra 1, Algebra 2, as well as volume, which would be like Geometry or Math Studies 1. Then finally, we get to doing our most recent stuff, which is our derivative, which took us seconds once we had it written in the expression given to us in Part C. Then we set that derivative equal to 0, which is our most recent lesson, to find our x, and then some substitution to find our y. And then finally, putting it back into some expressions, which was sort of like geometry and algebra all put together there. And that's what's going on here. Now, this would be a question. It's 13 marks. It should have taken us about 13 minutes. And it would be a paper 2 question, meaning that it would be on paper 2 of the IB test, which are usually the longer questions. There's usually only about 5 of them. So this would be one of 5 questions, perhaps, on an old IB test. All right, we will do more practice on applications of derivatives next class, and we will have a test coming up shortly on this.